lecture, and specifically to Professor Yashab Padhi from University of Minnesota, who has kindly agreed at short notice here. He came to here for something else. We met here and I requested him, and readily actually he agreed to give this lecture. It will be really very, very interesting and illuminating for all of us, because he is giving a lecture on a very, very relevant topic, and based on all his work, research, and whatever that he has done. With these few words, I will now request our Honorable Vice Chancellor, Professor Ashok Mahapatra, who is a distinguished doctor and excellent researcher, to say a few words about our university. Professor Mahapatra, please.
Good evening. Welcome to this distinguished lecture, Professor Acharya, Dr. Ganpati Panda, our all the participants, and our esteemed speaker. It is indeed a great pleasure that Dr. Acharya is organizing the excellent lectures, which will be not only heard by the participant, it will also put in a web YouTube so that the entire world can see all these excellent lectures. I think in last 1 year or so, we have more than 15 lectures or so, and they are all distinguished people in various fields from different part of the world. I think it's an excellent step taken by Professor Acharya and local chapter of engineering, and I congratulate them. Coming to our university, which is a part of the partner, our university is a very young university, less than 25 years. And in a period of very short time between 2007 and now, it has an impact all over the India and the world. And today we are only recognizing about 16 people, those who are top 2% scientists of the world. And last year we had 11, this year we have 6. So university has lived up to its expectation with its vision with which it was started. First thing was quality education. Second was the vision of 2007 was socially concerned issue. And third was local and international issues. Today, when you look back 20 years or so, or 25 years when the ITR started and the journey in the last 25 years, we see that a lot of things have happened. We have now 10 institutes. This year we are starting veterinary. In last 4 times evaluated from 2009, 15 and 23 times evaluation, our university ranking A++. This time NAC ranking is 3.88 out of 4. Previous ranking in 2009 and 2015, it ranked A++. If you look at the hospital and engineering side, our engineering college rank by NRF ranking, it's about 18 and university is 16. And medical science is 18 and engineering 27. And management, all these are now recognized schools under the SOA banner. So I think the university has lived up to the expectation of the people. And now more recently, Dr. Acharya and we have fortnightly so-called lectures. We have arranging lectures for the benefit of the people, and the lecturers are the top people of the world, different field. So I think this is a very good step. When I was in AIM started in 1980s, monthly lecture. Every month you used to have a lecture which was delivered in our auditorium, and all the faculty and resident and students are supposed to come. So those monthly lectures were given by different people. It was not CPC. Excluding that lecture, you used to have clinico-pathological conference on the brain of a individual or a body of an individual autopsy. So that is CPC, like the Harvard University CPC. But we had distinguished lecture by different people. So it is a very good step, and I must thank Professor Acharya for initiating this under the INE Odisha branch. And we have top people. I being a medical person have enjoyed. Many times I have left towards the end for something or other reasons, but I participate at least 90% of lectures, and another 10% I must have waited, seen about heard 75% of the talk. Last part I must have made for some reason or other, but I think these are excellent. And I must thank our speaker who had come a short visit to India, and on the request of Dr. Acharya, he has agreed to deliver this lecture. It is a very great job in his behalf, because educating others is getting away the darkness of the students. So I thank our honorable speaker to accept our invitation by Dr. Acharya to enlighten us, educate us, and motivate us in his experience what he has gained over last many decades. Thank you very much. I must again thank Dr. Acharya and our speaker who is going to deliver this distinguished lecture series of SOYA and IMT and a local chapter INE of Odisha. Thank you, thank you, thank you very much, sir. Back to you.
Thank you so much. And anybody actually from our IEEE Bhubaneswar chapter would like to say something about this chapter?
Sir, Ganpati Panda sir is there. He will speak. No problem.
Okay.
Yes, sir. Ganpati Panda sir has the founder.
Anyway, this
Sir,
chapter.
I request Ganpati Panda sir to speak few words on IEEE, sir.
Panda, can you speak? That is what she is requesting you. Would you like to speak something? Professor Panda?
Otherwise, Renu madam, you can speak. You are
No,
a
sir,
very
he is the founder. Sir is the
part of,
founder, sir. No.
This chapter.
I request.
Thank you. Good afternoon to all of you. I'm really privileged to introduce Professor Keshav Kerpadi.
You are not fully visible.
Yes. Is it audible, Professor Keshav
Audible you are.
Kerpadi? Yes. Thank you, Professor Mahapatra, Vice Chancellor, and Professor Damodar Acharya, distinguished honorable professor of the country. I'm very happy and lucky to introduce Professor Keshav Kerpadi, whom I knew when I completed my PhD in 1982. He completed his BTech in the same department. So I was very much knowing him since then. I was in touch with him for many, many years. He, from IIT Kharagpur, in 1982, after completion of his BTech, he went to US to pursue his MS. He completed his MS in 1982. The Department of Electronics and Computer Engineering, University of Minnesota. And in the same university, he completed his PhD program in 1988. He is a master in the field of VLSI signal processing. The whole world knows his contribution. He has 34 US patents and 700 research articles, which is very rare in this field. 700 articles. Till then, he is continuing his research, and presently he is working in very advanced field. His present area of research work is hardware security, and he is implementing the deep neural network in VLSI, which is very difficult.
Parala, I can't use my hand.
So successfully,
No, I want to hear computer locally. I can't hit that.
Now it is better.
Okay, so he is still working in the same area, in the area of hardware security and deep learning implementation in VLSI. He has written a very popular book. Worldwide, people are following in the area of VLSI signal processing. In 2013, he got the Distinguished Alumnus Award of IIT Kharagpur. He is a fellow of so many academies, including IEEE, which is very rare. He is very active in research, but as I know, he is a very simple person and having a good heart. So I'm really happy that he will be speaking today in very interesting area of accelerator architecture for deep neural network and also on homeopathic encryption. I'm sure the all participants today will be immensely benefited by his excellent lecture to be followed. Thank you again for giving me the opportunity to introduce the renowned Professor Odia, Professor Kasab Kepari, who has established in the US, particularly at the University of Minnesota, Minneapolis, US. Thank you.
Thank you, Professor Panda, for introducing our distinguished speaker today, Professor Keshav Padi, whom I have seen as undergraduate student in our so-called Kalinga Samaj meetings. That time I was a faculty when he was. Anyway, it is really a pleasure to have him with us. I will now request him to make his presentation, and also we'll get a big excuse that after a few minutes I will not be really available here because of some other urgent work. But I will request Professor Panda or Professor Sharma to take it forward so far as Q&A is concerned.
Sure.
Thank you. Thank you.
Okay, can you see my slides and hear me?
Absolutely, very clear.
Okay, very good. Thank you so much, Professor Acharya and the Vice Chancellor and Professor Ganapati Panda and Professor Sharma as well. It is nice to see you on the internet, and it's a great pleasure to be here today to briefly talk about my work, but really to talk more about where the field is and where the world is moving with respect to AI and ML and these kinds of topics. So thank you so much. So let me begin with, so what we are seeing is the continuation of the fourth industrial revolution as well as the beginning of the fifth industrial revolution. So this slide lists in a way where the world has evolved starting from 18th century. So the first industrial revolution was all about steam engines and replacing horse and human power. And second industrial revolution was mostly about steel, electricity, combustion engines. And so that's past. So the big thing that happened in third industrial revolution is the digital revolution, evolution of computers and information technology. So that's really the big thing from about say 1980s to probably about 2000. So 20 years or so, we saw a lot of things happening during the third industrial revolution. So that was a big revolution. In fact, the Google started right around at the end of that. Amazon started at the end of that period in about 2000 or so. So what we are going through now, starting with beginning of 21st century, is the fourth industrial revolution, which relies on all the technologies that we saw in third industrial revolution. So what are the big things happening in fourth industrial revolution? AI, artificial intelligence, robotics, Internet of Things, IoT, blockchain protocol, crypto. Crypto is some of you are hearing about Bitcoin and things like that. Okay, so the technologies that are driving on these markets are robotics, AI, augmented reality, virtual reality. So these are the big things in the fourth industrial revolution. While we are still progressing through the fourth industrial revolution, we have just begun fifth industrial revolution, where the goals are personalization. So you may be hearing these words, personalization in many ways, whether it is a recommender system or a personalized medicine. Or even when you access the web, the links that are recommended to you are personalized to your past history. So deep multi-level cooperation between people and machines. So that's kind of what we call human-machine interaction. So that's a big part of fifth industrial revolution. And the last word that says here, consciousness. And we of course know that machines are not live. Okay, machines are not live like humans, but they can come very close to how a conscious or live person would behave. So surprisingly, the power of computers and AI systems have come very close, almost as close as how a human being would behave. For example, they can carry out a 45-minute or an hour conversation non-stop with a human being in a coherent way. So that kind of tells you the power of computers today, the power of natural language processing, NLP. So the third industrial revolution really was possible. So I'm talking about the period 1980 to 2000. And you could think about, okay, Intel first microprocessor, 1971, 4004 microprocessor. So that's really what was the beginning of this electronics revolution and the computer revolution. But that wouldn't have happened had it not been due to the pioneering contributions of so many electrical engineers and computer scientists. So I've listed just a few to give you an idea. Turing and von Neumann, big contributors in field of computing. Shannon, Claude Shannon, in field of information theory, that really laid the foundations of data transmission and the capacity of channels, channel capacity. Bardeen, Bratton, and Shockley, working at Bell Labs, invented the transistor in December 1947, for which they got the Nobel Prize in 1956. And Jack Kilby, working at Texas Instruments, the invention of the integrated circuits. So nothing much happened there was a 12-year gap between the invention of the transistor and the integrated circuits, 1959, for which I got the Nobel Prize in physics in year 2000. And Noyes also considered a co-inventor of the integrated circuits. That led to the first Intel 4004 microprocessors. So a lot of technology being developed prior to that fourth industrial revolution. So what we are observing is the explosion of data. And these bullets are a little bit old, but still they are going to tell us about the growth in data. So I've taken a few bullets here. 100 zettabytes of data to be stored in cloud by 2025, and that's 50% of all data. 7.5 billion people to store data in cloud by 2030. Volume of healthcare data to grow from 153 exabytes in 2013 to 2000 exabytes in 2020. And 4 terabytes of data collected per day from a connected car and you multiply that by number of days and number of connected cars on the road. So certainly we can all see the growth of data in an explosive manner, far beyond what we would call Moore's law. Moore's law in integrated circuits, doubling the devices in 2 years and later in 18 months. And the data that we are talking about now continues to explode every 3 months. So that's what is the scale of data explosion. So today, a big part of artificial intelligence and machine learning is deep learning. Deep learning everywhere, and you think about who is inventing deep learning, advancing deep learning, and using deep learning. So there are a lot of these companies listed, and you can recognize many names: Google, Apple, Facebook, Amazon, Microsoft, IBM, Intel, Baidu, Alibaba, Tencent. These are big companies in China. I didn't list many hundreds of startups working on deep learning. And these are a few applications that I have listed here: object detection, image classification. Image classification is really what made deep learning famous and usable in all these applications, deployed worldwide, starting with ImageNet contest in 2012. Okay, natural language processing. A lot has happened in the past many years, and this field really has advanced so much. And I'll go through a couple of examples. Smart cars, smart drones, augmented virtual reality, robotics, as well as robots with personalized intelligence. Agriculture, surveillance, security, biomedical healthcare is big, very big. When you think about AI in healthcare, this is an area where a lot is happening, both to assist the clinician as well as to monitor the effectiveness of therapy. So there is a lot happening in AI in healthcare, as well as developing personalized healthcare. So healthcare is just tuned to that specific person, not just the whole population of patients in that group. So a lot of applications. It looks like a one slide, but think of these as a single line could be $10 billion market. So there is a tremendous demand. So this is a slide that is talking about the ACM Turing Award given to Bengio, Hinton, and LeCun. Bengio, Hinton, and LeCun. So yeah, so Bengio from Montreal and Hinton from Toronto, and LeCun is head of AI in Facebook. So this is a quote from ACM, fathers of deep learning revolution received ACM Turing Award, ushered in major breakthroughs in artificial intelligence. Okay, so so this is a slide that I took from a review paper that I wrote with my PhD student, published in this IEEE Open Journal of Circuits and Systems a couple of years back. So this slide shows a historical perspective of these neural networks. So nothing really much was happening. It was a dark age until say 1943, when two neuroscientists, McCulloch and Pitts, developed the first neuron model called the McCulloch-Pitts model. And that led to the work on perceptron by Rosenblatt in 1958. And so this was a major invention at that time, had really all the power, a lot of the power in AI in 1958. But some of that work really was paused by so-called this paper that Minsky wrote, Marvin Minsky at MIT. He wrote this paper that shows that the perceptron cannot classify a simple exclusive OR problem. So if we have data and we are computing the exclusive OR of that data, binary data, that cannot be trained by a perceptron, because perceptron is a linear model. and XOR is a nonlinear operation. XOR cannot be, XOR data cannot be separated by one linear hyperplane. And so that kind of paused this field for a while until it picked up really by the development of multi-layer perceptron. So instead of one layer perceptron, the multi-layer perceptron could then solve the XOR problem. So there was this gap here, so 69 to 86. And in between, there was some work on training by Verbose on back propagation. Japanese visual neuroscientist came up with this new neocognitron model that eventually led to that was the inspiration for artificial neural networks. So all of that, I won't go through all of these, but there was Boltzmann machine by Hinton and Janowski, and recurrent neural network by, this was PhD thesis of Michael Jordan at Berkeley. Well, that was his PhD thesis at UC San Diego. Okay, so now on the faculty at Berkeley, California. So Jan LeCun was working on LeNet at Bell Labs on digit recognition. People didn't believe him at that time. Nobody really believed in deep learning until 2012, where in the ImageNet contest, deep learning, or the AlexNet, who was a PhD student of Hinton at University of Toronto, the AlexNet outperformed all other models. So a lot has happened, long short-term machines, LSTM, graph neural networks, lots of different kinds of deep learning models apart from AlexNet 2012. So this is really, okay, let me just take a step back and say that we can think of the beginning era as the first phase of the neural network. We can think of what going on during 1980s. All this period was the second phase. The work on RBM, Hopfield. Hopfield came up with Hopfield neural network. So 1980s, we can think of that as the second phase, and then everything stopped. Everything really stopped. There wasn't much happening from 1995, 1996, all the way until, well, really until 2009 or 10. So why is that? Well, so these models were powerful, but the computers were not powerful. Computers were not powerful to train these models. And that all changed with NVIDIA. When NVIDIA came up with the GPU, that was sufficient to train models like AlexNet. And using 2 GPUs, Alex Krizhevsky was able to train the AlexNet that outperformed all other models in 2012. And at that point, all other classical computer vision algorithms really were sidelined in a way. Okay, since that point, we saw a lot of different more improvements by Dropout and new models from Microsoft called ResNet, from GoogleNet, this BGG out of Oxford, and some network like UNet coming out of Europe for biomedical data analysis, and more recently graph attention network. So this is kind of a one slide saying how this field has evolved over last 70 years or so. So the number of models continues to grow. People are trying to come up with different models. So I've listed a few. This slide taken from the Asimov Institute, zoo of neural networks. This is so I've listed a few. Autoencoder. Autoencoder is the encoder used in generative adversarial networks, or GANs, and that's used in a lot of designing fake. You may have heard of fake news, fake video. So these are all based on this principle of generative adversarial networks using some kind of autoencoder or variable autoencoder. There are other models here, Markov chains. We talked about Boltzmann machine briefly, alluded to that. We didn't really discuss. Restricted Boltzmann machine is slightly different. Instead of being fully connected, all these visible neurons are not connected to each other, and the hidden neurons are not connected to each other. Only connections from visible to hidden are allowed, unlike Boltzmann, where all connections from all neurons to all neurons are connected. Deep convolutional network, deep convolutional inverse graphics network. So these are just a few, and there are so many. So what is exactly AlexNet? AlexNet is a network of 5 convolutional layers, and 3 fully connected layers. So it takes an image, red, green, and blue RGB with 3 feature maps, each image sized 227 by 227, and that leads to in the convolutional layer 1, it outputs 96 feature maps of that image size. Convolutional layer 2 generates 256 images, 256 feature maps or images, processing 96 input images. With that image size, number of feature maps or images increases to 384 in the third layer, and then 384, but then it goes down. So you can see the number of maps has increased and then gone down to 256. At that point, we flatten that, and that multiply this out, that becomes 4096 neurons, and fully connected layer 6. Then fully connected layer 7, 4096 neurons, and 1000 layer neurons, and fully connected layer 8. This is a 1000 class classification. The images can belong to one of the 1000 classes, and each neuron would compute the probability that the input image belongs to that class. And then you can pick up the highest neuron with highest probability as the class label. So a lot has happened beyond AlexNet and subsequent networks like ResNet, BGG, GoogleNet, and so what really are the big things that happened after that? So these models called transformer models work by leveraging something called attention. So when you hear about that attention, that's really the big part of these transformer models that came out of Google. This is a powerful deep learning algorithm first seen in computer vision models. So the transformer model called BERT came out of Google, and so you can see this BERT listed here. And then this GPT came out of OpenAI. OpenAI is a AI research organization. But beyond that, we are seeing newer models called GPT. These are transformer-based models, and many versions. Second generation GPT called GPT-2, then the third generation GPT-3. So a lot is happening in this field of natural language processing, and this is an example of the power of AI. The power of AI today. So, for example, this tool called DAL-E1 for the first generation and DAL-E2 for the second generation. This is a tool from OpenAI that can create an image from text. So if we, for example, prompt a text, an armchair in the shape of an avocado, and it will give you many, not just I listed 4 here, taken from the website of OpenAI, but it will give you, if you are not satisfied, keep generating more and more. So that's the power of AI. And then to give you another example of the power of AI, this is the first cover of a magazine generated by an AI program. So the same DALL-E 2 that I talked about can generate this cover of the magazine Cosmopolitan. If you prompt the words, these are the words, a wide angle shot from below of a female astronaut with an athletic feminine body, walking with swagger towards camera on Mars in an infinite universe, synthwave digital art. And that, if you put these words into DALL-E 2, that's the cover you get. And that became the first digital cover of a magazine generated by AI, not by an artist, and generated only in 20 seconds. So that kind of gives you the tremendous power today that these programs have. The programs now are able to write papers and submit to conferences that are accepted by the program committee. And so that kind of tells you again the power of these programs. And they can continue conversation in a cohesive, coherent way with human beings for a very long period of time. So that's really a tremendous amount of progress. So that's great. That's great. But what really are the bottlenecks in training these models with many 100 billion parameters? So if you think about a round trip flight from New York City to San Francisco consumes 900 kilogram of carbon dioxide emission per passenger. Average human life, 50,000 kilogram of carbon dioxide per year. Average life of US person, 16,400 kilogram of carbon dioxide per year. If you take a car, you run the car for 10 or 15 years, that's the life of the car, that's 57,000 kilograms of carbon dioxide emissions. And if you take these state-of-the-art language models trained using 200 billion parameters, that's 75,200 kilograms of carbon dioxide emissions. So when we are training these hundreds and hundreds of models, it's really consuming a tremendous amount of energy. The exponential increase in energy consumption. The data to train models doubles every 3.5 months. So if you thought about the number of transistors doubling with Moore's law in 24 months, later became 18 months. So data doubling in 3.5 months. Time to train the ImageNet, that became the precursor to everything happening in 2012, is equivalent to emission of as much carbon dioxide as New York City generates in 1 month. So this is a model called ZSAT, has a memory footprint of 600 billion weights, 28 terabytes, and this requires 22 TPU, tensor processing unit years out of Google TPU. And this is another example. If we run the GPT-3 natural language conversation on a Google Pixel 4 processor with a 10.4 watt-hour battery, that will be depleted in 4 minutes. So GPT-3 has been trained using 420 billion words, and compare that to a 6-year-old child who has been exposed to at most 65 million words. So very powerful, but very energy hungry when it comes to training these hundreds of billions of parameters. So I'll talk briefly. I don't want to go into a lot of detail. The details are all in the papers, but I'll briefly talk about a couple of ideas from the work that we have been doing. So I'll talk a little about this technique called permuted diagonal neural network, PermDNN, that can reduce energy during inference. I'll talk about this interleaved gradient computing. So this is an idea that can reduce energy during training, and this work on layer pipe that can also reduce energy and latency, the speed of training. So these are all published papers published in Micro 2018 and Circuits and Systems Symposium 2020. The layer pipe is published in ICCAD, conference in the computer-aided design community. So Google TPU and NVIDIA GPU are still the most powerful engines. Google has its tensor processing unit, uh, which is which contains numerous systolic arrays for matrix multiplications. Google TPU can be used in the cloud as well as the edge device. That's kind of device that you are holding or near you. Cloud is you upload the data. Think of that as a big server. NVIDIA GPU. So that's also a very powerful engine. This is an example from Alibaba, so-called Hangguang 800. And at that point in time, 3 years ago, they claimed that was the most powerful inference chip that could classify images at 78,560 images per second, using 500 images per second per watt, based on this model called ResNet 50 out of Microsoft, with 50 layers. ResNet 50 means 50 layers. So deep neural networks are getting deeper and bigger. And so if you look at how the ImageNet contest evolved from 2012 with AlexNet, the winner in 2014, VGG, and then GoogleNet. So GoogleNet was winner, VGG was second winner. And ResNet was the winner in 2015 out of Microsoft. And so the number of layers increased from 8 to 152, number of convolutional layers 5 to 151, and fully connected layers are 3311. If you look at the number of weight parameters, these are the parameters that need to be trained. The word trained means need to be updated. That means you take the old weight, add some delta weight to that to get the new weight. And the delta weight or the change in weight is computed by some kind of a algorithm like a gradient algorithm. It could be stochastic gradient descent, which is typically used, but there are other algorithms as well. So if you look at the number of weight parameters, these vary from 50 megabyte to 500 megabyte. So lots of parameters. And the one of the bottleneck in training these is moving data between ALU and memory. So that's a big, lots of power and lot of latency, delay and energy bottleneck in moving data between memory and ALU. So this idea, what is the main idea behind permuted diagonal neural network? So that idea is inspired by error control coding, in particular the LDPC codes, low density parity check codes. These are used widely in wireless communication systems as well as wired communication systems. And when I was working on this topic, I didn't develop the code. We were working on hardware architectures. But really what I want to point out is the symmetry. Rather than having these ones in the parity check matrix located here and there, this is the symmetry. So you start with this particular place 1, we reach the end, we circularly come back to beginning, then go to the end. So this whole thing, you think of that as that whole thing is as one diagonal. And this whole thing here reaches the end, comes back, and then comes here. So that's another diagonal. That's like 2 diagonals. And these are in a structured manner. So that really led to hardware-friendly LDPC codes. So this is called the parity check matrix of the random LDPC code. So instead of having random connections between the input neurons and output neurons, how can we bring that kind of sparsity in a structured way? So both of these matrices that you see are sparse matrices. So this 8 by 4, 8 neurons on the output layer, 4 neurons on the input layer. So 8 by 4 matrix, but the number of non-zero elements is only 8. So that's kind of a sparsity by factor 4. Instead of having 32 non-zero elements, we have 8 non-zero elements. But these elements are all stored here and there. That's called random sparsity. If you look at the structured sparsity, the so-called permuted diagonal network, so the bottom 4 by 4 submatrix, these are located on the diagonal. So that's what I call a permutation value 0. And what we see on the top submatrix is called a permutation value 2. That means you take the diagonal elements, shift right by 2. So that comes here. That's here. Take this diagonal, shift by 2. That comes here. Shift this by 2. 1, circularly shift back 2. And shift this element by 2. Circular shifts back 1 and 2. And so what's the main advantage of having this permuted diagonal matrix? So in the random sparse matrix, I need to store the column index and the row index and the value. So for example, I need to store the value and the row index. So for example, if I want to store on the first column what's non-zero, that's 0.4, row number 4. Second column what's non-zero, 1.2, row number 1. Third column what's non-zero, minus 0.5, row number 3. So this thing, so I need to store these 8 things, 4 things, row index 4 things. In this example, I only need to store the 4 values, these values, and only one number for the permutation value. Permutation value is 2. So that's all I need to store. So in a P by P submatrix, where each number is represented by qubits, so I can reduce this memory space from 2pq, so 2p times qubits, to pq plus that permutation value by log qubits. So that's the savings. And so I won't go into more, but that kind of approach can lead to 3 to 5 times higher throughput, 6 to 9 times area efficiency, 3 to 4 times energy efficiency. So there is a lot of detail. We won't talk about that today, but the paper in Micro 2018 is already published. So let me just change the topic, and how can we reduce the energy consumption in training the neural network. So what exactly is going on in the training? So the training happens to be happening through this something called back propagation. So this is called the inference or the forward pass. So I start with input, I compute the output of the first layer, second layer, third layer, fourth layer. That's the output. I compare that result with the ground truth. That is an error function. I compute an error. You can call that loss functions. And then what is propagating backwards? Going backwards is the gradient of the error with respect to the activation function. So these outputs are activation functions, and that gradient is propagating backwards. As it propagates backwards, that gradient is also used to compute the gradient with respect to weight. And the gradient with respect to weight is what is used to update these weights. So that's really what we need to update. So the whole idea of this interleaved gradient computation is, instead of computing these gradients first, let's say it takes some number of cycles, and then I compute the gradients with respect to weights, and then it takes some number of cycles. So what happens by traditional scheduling to compute the gradient with respect to activation function and then compute the gradient with respect to the weight functions. So what you see here is this, in this computation, this parameter delta, we fetch that delta from memory, and then we complete this. And then when I get to gradient computation with respect to weight, I need to bring that delta again from memory because I've lost that delta. So the whole idea of interleaved gradient is, why compute the first gradient and the second gradient? Why not compute one at a time? Just keep one gradient here, one gradient with respect to activation, one with respect to weight, one with respect to activation, keep toggling. And if I keep toggling, then the same delta can be used to compute both at the same time. So I can reduce the memory access by a factor of 2. And there is a lot more going on. So that's kind of showing you one reuse of the variables that I am bringing from memory to the local memory. But there is a lot more going on here. So when I am computing these gradients, I am using this weight. So these weights are being, when I fetch the weights stay in the processor, and then they can be adapted. They can be adapted in the same processor. So there is a lot of local reuse. The basic ideas of reducing energy or memory access is locality, local reuse. These were the ideas that led to the systolic array by H.T. Kung, and one of Kung's PhD student at Google designed the Google Tensor Processing Unit, which has in the version 1 had 4 systolic matrix multipliers. So to give you a little more insight as to what is going on. So we are computing the gradient with respect to weight using an output stationary systolic array. So that's shown here. So these gradients stay here, and output stationary means, well, these words have some meaning. That means the gradient for this cell continues to be accumulated right here. So the input delta is coming in, activations are coming from bottom. To compute gradient with respect to the activation function, same delta, the delta you see here, same delta, fed from the left, zeros fed from bottom, and the weights are brought in and they're in these processing elements. And when I adapt these weights to the next weight, the gradients are already there in the same cell, these gradients, and then they can be adapted by interleaving. So the idea is to toggle between one clock cycle to compute G, another clock cycle to compute delta E, delta A gradient with respect to activation function. So the processing elements keep toggling between two modes. And if they toggle between the output stationary and weight stationary, so the weights and the gradients are in the same PE. So as soon as the gradient is complete, I adapt the weight. Deltas are brought in once, used twice. So lots of savings. That's what is called interleaved gradient scheduling. And I won't talk about a lot more about how it is applied to the convolutional neural networks. That's quite complex. We won't talk about that. But if you look at the savings in the memory access, so compared to the input stationary approach, weight stationary, output stationary, this is interleaved gradient scheduling, we can see that it has the least memory access. The latency, how long it takes to compute the training or the back propagation, also has the least latency. Normalized performance with the network size. These numbers on the x-axis are the number of neurons in a fully connected neural network. And the next slide shows same memory savings and computation savings for two networks, VGG16 and AlexNet. Okay, so roughly speaking, we can reduce the memory access by a factor of 2. We can increase the speed, reduce the time to do the back propagation by about factor of 2 using that idea. So a third idea that I can talk briefly about is this idea of enabling parallel processors to do the training. And so if you look at what the training does, the back propagation, this is a highly sequential process. So we do all the inferences, compute the error function, back propagate all the way. So that's the critical path. There is no ability to create. So the computations of all of subsequent stages are dependent on the prior stage. And then when I back propagate from right to left. So again, that is dependent on the one on the right. So this is all a sequential computation. And so again, these are the main components I talked about. You compute this W times A, That's a linear computation, compute the nonlinear activation output, compute the gradient with respect to activation and gradient with respect to weight. So that whole thing is the back propagation. So there are so many loops that lead to sequential dependence that slows down the back propagation calculation. And we are interested in speeding up that back propagation calculation so we can reduce the latency. So the training loop is a typical signal processing structure. And we know a lot about how to speed up signal processing computations. So one idea to speed up that training is really to use delayed gradients. So if you think about this gradient here, to update the weight, instead of using the current gradient, use the gradient 4 cycles back. And same here, instead of using the current gradient, use the gradient 2 cycles back. So that's what is called delayed gradient. And delayed gradient is an idea that has been around for a long time, published in the transactions and acoustic speech signal processing. The ALMS algorithm is the delayed coefficient adaptation. So in the adaptive filter, we have an input, we have a forward filter, we get an estimate of the desired signal. The desired minus the estimate is an error signal, and using input and error, we compute the gradient and use that gradient to update the weight. So the previous weight plus some function of gradient is the next weight. Okay, what's the idea between delayed gradient? Instead of using this gradient, use gradient before m cycles. And that then is called delayed gradient, and that is suitable when the random process is a slowly varying process. If the random process is not changing rapidly, then the delayed gradient idea can work well. And that same idea in the context of training deep neural networks, in this case, this delayed gradient, I've introduced 4 delays and 2 delays, and I can retrain these to obtain interstage pipelining. So this is called variable delayed gradient for deep neural networks. I've delayed this gradient by 2 times n minus 1, and at the end 2. So the number of cycles that we need to delay is a variable number, is the largest from the beginning and smallest at the end, and that can lead to interlayer pipelining. So that's so using that kind of an idea, we can balance the workflow in a multiprocessor scheduling environment. So the top one here shows a similar paper out of Microsoft called Pipedream, and the one on the bottom shows the layer pipe, which is what we are showing. And if you look at this underutilized space, nothing happening in these spaces, and by using the systematic layer pipe, we have kind of eliminated the underutilization, means we have reduced the latency of training. Okay, so what is really happening today with respect to approaching towards consciousness? So these machines are becoming almost as conscious as human beings in the way they can converse, they can write papers, they can generate diagrams that are as capable as a famous artist. So what we see happening in next 10 years or so is really what we call pervasive general intelligence. So from artificial intelligence, the path to general intelligence. So what do we mean by a general intelligence system? That means these systems have the ability to think and reason with prior experience and knowledge. They can perform causal analysis, analyze with curiosity, and can speculate. The ability to memorize or recall past experiences, thought processes, associations, conclusions, and data, namely knowledge. The ability to process information and knowledge to support causal reasoning, curiosity, and speculation. So these are all the aspects of general intelligence. This is a very busy slide that I'm talking about what exactly, what are the fundamental knowledge required to achieve general intelligence, what are the enabling technologies, and then what will be the systems, and what are the barriers at each of these levels. At the fundamental knowledge level, what are the barriers? At the technology level, what are the barriers? At the system level, what are the barriers? So this slide, I could talk for an hour on this one slide, but let me just briefly read out a few things. So at the fundamental knowledge level, we are interested in designing machines capable of cognitive thought processes. So these are inspired by neuroscience. Solving the AI compute complexity problem using hardware, heterogeneous network accelerators. These networks should have the ability for prospective learning. All the learning that is happening today using past data is retrospective learning. So we need to move towards prospective learning that can make use of causality, curiosity, introspection, speculation, planning, decision making, and different types of knowledge representations in a hierarchical manner. So no clear pathway to human-like intelligence, intelligence with form factor energy consumption of the human brain, lack of emission-friendly training algorithms. Training algorithms are very, very energy hungry. At the technology level, we need to create new computational models for cognition, inductive biases that support cognition, that make use of causal priors, fluid intelligence, and meta reasoning and meta learning. That also can accommodate domain shifts. So a camera trained to monitor vehicles in New York City is not going to work in Mumbai. So these training algorithms must be capable of domain shifts. Neurosymbolic, that requires neurosymbolic computing, few-shot learning. Yeah, go ahead. Okay. And neural knowledge retrieval. So lots of systems that can make use of these general intelligence, transportation, cars that can reduce the energy consumption, smart cars, robotics, healthcare, neuropsychiatric disorders, personalized therapy, conversational AI. So this is really a big field in itself where the AI is moving towards GI. So this is kind of taking some of the bullet points from the previous slide, so I can probably skip that one. So I have completed first part of the talk. I can very quickly go through the second part. So there are this, when we think about post-quantum cryptography, anything that you are using today, we are using electronic transactions to pay by Apple Pay or Google Pay or Samsung Pay, or we are accessing a web using credit cards. All of these transactions are using so-called AES, Advanced Encryption Standard, that was standardized in 2001. But AES algorithms can be broken by quantum computers. There is a lot happening in quantum computers, and Peter Shor at MIT developed this algorithm called Shor algorithm that has shown that the factorization problem can be solved in polynomial time by quantum computers. And that means we need to have new standards that are quantum safe, that cannot be broken by quantum computers. So that really has led to this standardization process called post-quantum cryptography. Eventually down the line, that will replace the AES crypto system. And so the lattice-based PQC is most popular and is part of this Crystal, Skybird, Lithium, Falcon. So let me just say that. So this standardization, I think, yeah. So this standardization started in December 2016 by US National Institute of Standards and Technology. It started with 69 proposals, downsampled 3 rounds, and the final selected standards candidates were announced in July 2022. And for general encryption, the standards committee selected so-called Crystal Skyber. For digital signatures used to verify identities during digital transactions or to sign a document remotely, they selected 3 algorithms called Crystal, Dilithium, Falcon, and Sphinx Plus. So the point here was to say that out of those 4, Crystal, Skyber, Crystal, Dilithium, and Falcon, these 3 are based on the so-called lattice-based post-quantum cryptography schemes. Okay, so there is a need to maintain the privacy of data, whether it is patient's data, genomics data, bank data, financial data. So that's the post-quantum cryptography. And so computers that can, quantum computers, there is a lot happening. IBM just announced the 433 qubit processor called IBM Osprey, November 9th, 2022. This more than tripled the number of qubits or quantum bits compared to their prior design from 2021. So what they show here is the roadmap. They are going to develop quantum computers with 1386 qubits in 2024 and more than 4,000 qubits in 2025. So, so again, there is a need for quantum safe crypto systems. So what is homomorphic encryption? So all the time we are sending our data to the server or the cloud, and the cloud knows our data and creates the model. So here is what is homomorphic encryption. If I am going to do a 20 plus 10, I send encrypted 20 to this cloud, encrypted 10 to the cloud. Cloud knows it is an add operation. So it decrypts to get the plain text. These are the ciphertexts. So ciphertext is decrypted to plain text, add, get 30, this is plain text, encrypt, and send it back to the user. User will decrypt and get 30. So what's the harm in that? The harm is when people are sending valuable data to the cloud itself might be having interest in what model is being created. There may be another competing company that is trying to model a similar application. So we don't want, these users want all the computations of the machine learning to be carried out in the encrypted domain without ever decrypting to plain text. And that's what is homomorphic encryption. Okay. So there are 4 parts to the homomorphic encryption: key generation, encryption, evaluation, and decryption. Again, I'm not going through a lot of these things. So very, very quickly, all these, both post-quantum cryptography and homomorphic encryption are based on what is known as polynomial modular multiplication over a ring. Okay, this is an example of how we can multiply a polynomial ax and a polynomial bx over the ring x to power 4 plus 1. And so that can be computed by a systolic array. That can be computed. This is the dependence graph. The dependence graph can be mapped in this direction. That means it can be projected in this direction. That means all these 4 are computed by 1 hardware unit. These are computed by 1. These are computed by 1. So this can be computed by these 4 hardware functional units. So this is called a weight stationary systolic array. And then to reduce the latency, we can compute this polynomial modular multiplication in parallel. Again, I don't want to go through a lot of detail, but a lot of prior work that I have worked on long ago. And also in my textbook in 99, chapter 9, this fast parallel FIR filter, that idea can be applied to take the polynomial a of x, the even and odd coefficients, and filter them here using the even and odd of b. And we can reduce the latency significantly by using this parallel FIR filter approach. And so this can be adapted quickly to the problem of polynomial modular multiplication with some small change. You can see how this changed into that. So again, let me skip a lot of the details, but so we can transform fast parallel filter to the parallel polynomial modulo multiplier. Each delay represents left shift, which is a non-causal operation. We can introduce latency to make it causal or implementable. So there is a paper that's not yet published under review, but available. The preprint is available on arXiv on this number here. So this is kind of an approach that's used for post-quantum cryptography. But when we deal with homomorphic encryption, the degree of these polynomials could be 4,000, 8,000. And in that case, the best approach to use is the approach in the frequency domain, where we take the polynomials, compute the number theoretic transform, multiply them, and compute inverse number theoretic transform. So we haven't published this paper yet, or even submitted that paper yet, but that's the idea. And these are some of the block diagrams of the number theoretic transform. And this is number theoretic inverse number theoretic transform. We can map these into these systolic arrays. Systolic arrays are shown here for entity and identity. And this because the number of bits can be very long, that can be simplified by using what is known as Chinese remainder theorem, CRT. Again, without going through a lot of detail, these are some of the results for polynomial modular multiplication for 4096 point. Degree is 4096. And using, for example, if I'm using 192 bits without using Chinese remainder theorem, I would need 2 million lookup tables, 1700 DSPs, and 174,000 flip-flops in an FPGA, Xilinx FPGA device. But using this Chinese remainder theorem, we can reduce these numbers significantly. So we can also reduce the latency significantly. For example, the latency can be reduced from 400 microsecond to 38 microsecond using the Chinese remainder theorem. Using more and more parallelism in the number theoretic transform, we can bring this down as well. So people have been wondering, okay, is fully homomorphic encryption going to be real time? Can it be ever operated in real time? So the answer is yes. Using the proposed approaches, it can be operated in real time. It's going to be expensive. It's going to consume more energy, but it can be operated in real time using the parallel number theoretic transform approaches along with Chinese remainder theorem. So to summarize, I've talked about energy reduction in training deep neural networks. A lot remains to be done. So how do we develop architectures for training transformers? As I talked about, this GPT-3, BERT, these kinds of very powerful natural language processing transformers, recurrent neural networks, spiking and graph neural networks. There is a lot work is going on in my group, and literally by thousands of researchers worldwide. What we are seeing is a move from artificial intelligence to general intelligence, and that's kind of a big trend in research. I briefly talked about the fast polynomial modular multiplication in time domain as well as frequency domain using number theoretic transform, and much remains to be done in this area using hardware software co-design, and in particular to map specific fully homomorphic encryption algorithms like the BFV or BGV or CKKS. So let me acknowledge a few people. My former student who is a professor in Rutgers, Bo Yuan, he contributed to the work on PermDNN. Nanda Unikrishnan, my current student, who will join Meta on January 9th, worked on the two ideas that I described on interleaved gradient scheduling and the layer pipe. We have a number of students working on the homomorphic encryption. I have a student at University of Minnesota, and these are two of my former students who are professors. Yingje Lau, professor at Clemson, Chenmiao Zhang, professor at Ohio State, and he has a couple of students at Clemson. So we are jointly working on this homomorphic encryption project. So that brings my talk to an end. Thank you very much, and we can have questions and answers.
Thank you, Professor. Thank you so much. It was very, very informative and very, very elaborate and lucid presentation. I would like to invite the questions from the audience, please. They can unmute and they can put up the questions. Am I audible? Am I audible?
Yes, you are.
Yes,
Thank
we
you.
can hear you.
Thank you, sir. So I would like to invite questions from the audience, those who are present. Otherwise, I'll think that it was a very explanatory presentation. So I'm not finding any questions. They can put up in the chat box if they're not able to speak. I can check the chat box also.
Well, this is Radhakant Padi here from IIT Bangalore.
Yes, sir, please.
Yeah, I'm speaking from Uttar Pradesh, by the way. I'm somewhere there, but that I think is audible.
Yes,
So
sir,
is it-
you are very much audible, sir.
Fantastic talk of a lot of variety of things. But is it anything to do with the discipline specific, or it is in general valid for all sort of, all sort of neural networks basically? Where application to all sort of data, not necessarily with the image only. Is it something to do with that or not really? I mean, I'm a little confused about it.
Excuse me, could you please say it again?
Is it all the things that you talked about, energy savings and things like that, the training, the way you talk about intelligent way of gradient computation, is it specific to only image processing networks, CNN sort of thing, or is it something to do with all sort of networks?
Okay, so yeah, the question was, yeah, I believe it is generalizable, and because when we are computing the gradient, we are computing multiple gradients. So the work that we have published is for convolutional neural networks, but I believe this can be applied to recurrent neural networks, RNNs, as well as graph neural networks, GNNs. We have not published them, but yes, I believe when we are computing multiple gradients, and which usually we do during back propagation, yes, they are not just for CNNs, but they can be applied to GNNs and transformers. Because why is that? Because transformers contain many fully connected networks. And so definitely transformers are networks that can benefit a lot as well.
Is something to do with even spiking networks? Can you use it for spiking networks?
Yes,
Not
that is a good question. Yes. Spiking, so okay, so I mean, there are, okay, spiking networks. Let me just mention why spiking networks have not been as popular. I mean, they're gaining popularity, but why haven't they been as popular? Because nothing like ImageNet has existed. So the only reason AlexNet brought fame to these networks is because of the enormous data for the ImageNet contest. So we haven't seen, and of course the availability of GPUs and TPUs. So we haven't had that kind of a very big publicly available contest or data set to apply spiking neural networks. Okay, that's kind of a brief reason why that hasn't been applied. Okay, so can spiking neural networks, so it maybe, so okay, I believe that the layer pipe is more applicable to spiking networks. That's what I believe, because you think about the sequential dependence, the computations going on without a lot of ability to pipeline those. So I think the layer pipe is a good candidate for creating concurrency in the spiking neural network. But that again has not been published, and I am hoping to have a student work on that starting January. I have a visitor, pre-doctoral visitor coming from IIT Kharagpur to visit me, and so I would like him to work on that problem.
All right, got it. Thank you very much.
Thank you, sir. Thank you for your answer for the query. I would invite any other questions, or we will end up with a vote of thanks. So I'm not finding any questions, sir.
Okay, thank you very much.
Thank you, sir. It was a very nice presentation. Like you started with the machine learning and data analytics that's continued to explain, going to expand the fourth industrial revolution, and it's going to affect many of our aspects of the life, as you said. And you had explained very well how the energy consumption is increasing exponentially, and what are the powerful engines used by Google, NVIDIA, and what are the powerful interfacing chips. You have talked about deep neural computation bottlenecks like memory and the moving data between ALU and the memory. And you have beautifully explained about PER, MDNN, and intergrad, layer pipe, and many more, elaborately with examples. And as we know that machines are becoming conscious like human, you also touch the points and explain about PGI, like general intelligence, that human-like cognition, and barriers and the solution to various levels of PGI. You also talk about post-quantum cryptography and what exactly is a homomorphic encryption, and also talk about NIST and many more things. The talk doesn't end over here. It is the starting, sir. We look forward for future webinars from your end, sir. Thank you so much for all the audience and the phenomenal speaker. I thank on behalf of INA, IMMT, Shiksha Anusandhan, DIMTB University, and IEEE Bhubaneswar subsection. Thank you so much, sir. And thank you all for joining this evening. Thank you. Namaste to all.
Thank you. Namaste. Bye.
Namaste.